Okay. So now put a heading, line spectrum of a hydrogen atom. So basically, for example, when an electric discharge is passed through a discharge tube containing hydrogen gas, so we got that there is some light is passed, okay? And when the light is passed through the prism, so we get five lines, okay? That is the light spectrum of hydrogen atom. You can see that when discharge tube, there's a diagram in that also. So when the discharge tube in that hydrogen atom is there, so obviously if a light is emitted in that discharge tube is the hydrogen gas only. Are you with me?
Yes, sir.
Okay. When that light is passed through the prism, we got four lights. 410 nm means wavelength. 434 nm again another wavelength. 486 nm wavelength and 657 wavelength. On a careful analysis of hydrogen structures, it found that few sets of lines in the ultraviolet, in the visible range, in the infrared region. These lines were observed by different scientists. So basically, these lines observed by scientists, the spectral emission lines could be expressed in the form of general formula. There is one formula in which we can express the wave number, like wavelength we are getting. So the name in that we can get the wave number. What is the wave number? Can you explain it to me?
So wave number is the reciprocal of wave. It is represented by nu bar.
Yeah. No. What is the meaning of wave number? It's the formula for that. No?
Yeah. So
What
wave
is the
number nu bar is equals to 1 by lambda, 1 by wavelength.
no, wave number? I'm asking. Like what is the wavelength?
Yeah. Yeah, wavelength is like the length.
Distance between the two crests
Yeah, two.
or two trough
Yeah.
or length by an oscillation. That is the wavelength.
Yes, sir.
Now, a length by an oscillation is called as what? Wave
Wavelength.
number, wavelength, and one oscillation has how much length? That is also wavelength.
Yes. Yeah.
Okay,
That's also wavelength.
so that is also wavelength. Okay, so we have one formula which you have to learn. V bar, which is a mu bar, which is called as wave number, is equals to 1 upon lambda, is equals to RH in N1 into N2. So basically, what does this mean? What does this mean? We will come to one spectrum theorem, okay, in which we saw that when a atom or electron, when it travels from one, okay, my camera is on. When an electron travels from one uh, one line spectrum to the another line spectrum, then it shows some wavelength.
Yes.
That wavelength can be calculated in the form of this line spectrum. Emits special emission spectrum. Did you get it? No, you
Yes,
didn't
sir.
get it.
Got it. Got it. Got it, sir. Got it, sir.
What I told you, can you tell it to me? What I told you.
Like, like you told about the line spectrum, and okay, and you told about the formula that nu bar is equal to RH into
Hmm.
1 by n1 square minus 1 by n2 square centimeter inverse.
Yeah. So, for example, there are some this thing. Okay, Lyman is the first series, okay, of the emission series, and Balmer is the second partition bracket P5. We have these five series. Now, if a electron, because of the electricity, it got excited. If it is coming from 2, 3, 4 to the 1, okay. For example, what does this mean? This means that when you will give electricity or energy to the electron will get excited.
Yes, sir.
Yes.
Yes, sir.
And if it will get excited, it will get unstable. It will go to the up level. Okay,
Higher,
so I'll explain this.
higher energy level. Higher energy.
Yeah. So for example, this is N1 and this one is N2. This one is N3. This one is N4, N5, and
And
okay, N5. Okay. Now, for example, the first series is called as what?
Lyman,
Lyman.
Lyman. Versus Lyman.
This one is Lyman. This one is Balmer.
Balmer,
This one is Passion.
Pascal, Pascal,
This one is Bracket.
Pascal.
Bracket. And this one is Peter. Peter. Okay. Now, if a electron get excited to the bracket, means N4, and if it is coming to the N1, like it was N1 area, it get excited and it came to the Lyman area, then the wavelength is gonna be the ultraviolet wave.
Yes,
Got
sir.
it?
So Lyman series lies in the ultraviolet range. Balmer lies in the visible range. Then Pascal, Brackett, Pfund, and Humphrey lie in the infrared range.
Infrared, yes. So whatever the visible, like the light which is visible, that wavelength is always a second electron when it is emitted and it comes to the again back to the N2 series. Then the rays, the wavelength which is created is always Balmer. Got it? No.
Yes, Balmer. Yes, sir.
Yeah. So this is visible range.
Visible.
This one is visible range. Now, what is Passion and this one is? This like Passion is infrared and bracket and prefund is far infrared. So we'll write infrared according to your. Now, what is N1 and N2 and N3? N1 is basically the what we can say series. Okay,
Yes, sir.
okay,
Yes.
series of lines we can say series of lines.
Yes. Series of line when the electron comes from higher energy level to lower energy level.
Lower energy. Okay. So this is what we learn in that. Did you understand?
Yes, sir.
Okay. So we have the one formula. Can you write it down with me? This whole thing after the infrared, and then I will tell you what to write. That is V like wave number. I'll write here. V bar, which is called as wave number, is equals to RH into 1 upon N1 square minus 1 upon N2.
So so nu bar is equals to 1 upon of lambda.
1 upon of lambda. Well, that is a simple that we have now.
1
Okay.
lambda. Yes, sir.
And what is the formula of RH? Like what is RH? RH is called as
Rydberg constant.
Ray, Ray, Rydberg.
Yeah.
RYDBERG Rydberg constant. Okay. Got it?
Yes.
And what is the N1? N1 is the we can say the electron without electron orbital state. Electron, or we can say electron orbit, electron shell, no, electron orbit, electron orbit without excitation. So, for example, it is in the first, it is without excitation, it was in the first, then that is one. Okay, and N2 is here is electron state after excitation, means from where it is coming from. Okay, so no matter that Lyman, no matter the electrons in the first orbit, it will go to the anywhere. When it will come back, it will always releases the ultraviolet ray. Means it will always releases the higher frequency wave.
Yes, sir.
Are you getting this point?
Yes, sir. Yes, sir.
Means if like Balmer is a visible, no?
Yes.
If that electron goes to anywhere, it will always give visible ray.
Yes.
Means we can see the color.
So I mean, if electron comes from 5 to 2 or 4 to 2 or 3 to 2, it's always in Balmer series, and in Balmer series, it is always in the visible region only.
Yes, yes, correct. So we have one question. Will hydrogen atom electron which is excited, can we see that light?
Okay. So when the hydrogen atom, the electron gets excited. When the electron gets excited, then we're saying that we can see. But since since here it's coming from a higher energy level to a lower energy level, so then only we can see. But lower to higher, I don't think we can see.
Yes, you cannot see. Okay. No, you cannot see the light coming from any standard higher hydrogen electron in the electrochemistry. Okay.
Yes, sir.
Perfect. So now write it down one thing. On passing an electric discharge tube through a gaseous hydrogen atom.
Huh?
On passing on passing through a gaseous hydrogen atom, hydrogen molecule hydrogen molecule get dissociated to produce energetically energetically excited hydrogen atom that emit that emit that emit light light no that emit electromagnetic radiation, sorry my bad, that emit electromagnetic radiation of this discrete frequency. Discrete means different frequency. Okay, now I'll give you the question. Calculate calculate the wavelength, comma, calculate the wavelength, comma, wave number, comma, frequency, comma, energy
Yes.
of the Balmer line of the Balmer line corresponding to Paschen line. Corresponding to Paschen line. So what we have to calculate? We have to calculate this thing. What? We have to calculate wave number. We have to calculate wavelength. We have to calculate frequency. We have to calculate the energy. So we know that wave number is equals to RH. Sorry, 1 upon RH, my bad.
No,
1
no, no.
upon,
It,
no, no, RH. Sorry.
RH is equal to
RH
RH
is
to,
equals to RH
no,
into
not equals to RH into
1
upon of
upon.
1 upon of N1 square minus 1 upon of N2 square.
So we have to calculate it that if a line electron was at Balmer series, but now it went to the Paschen series, then what wavelength or what frequency or what energy will it have? So
Uh,
I told you
From
that if an electron is in Balmer series,
no,
it
no.
will give a visible range.
I mean, basically, it's coming from past 10 means n is equal to 3 till Balmer and n is equal to 2. That means n1 is 2 and n2 is 3.
So means like electron is in right now Balmer, no? Means the existing state, the home of electron is in Balmer series, but now it got excited to the Paschen series and now it's coming back to the Balmer series. Are you getting this?
Yes, sir. So from past 10 it's
So
coming to
N1,
Balmer.
yeah, N1 is 2,
Yes.
N2 is 3.
Yes.
Now we know that we can calculate the wave number and wavelength easily. There is no problem. But how will you calculate frequency and energy in that? Because we know that the frequency formula is, what is the frequency formula in
C
terms of
upon
this
C upon lambda.
C upon lambda? What will you write C value? So because it's a visible range light speed is,
3 into 10 power 8 meters per second.
so you have to put that thing. Are you getting this? No.
Yes, sir.
Then you will get the frequency. And when you will get the frequency, you have to calculate the energy also. What is the energy formula?
Um, hc by lambda or hc, yeah, hc by lambda.
H C by lambda. And we know that C by lambda I can substitute as mu. So it will become E is equals to H mu.
Mu.
So we got this thing and we can easily. Can you do it at home?
Or or now itself.
Now, it will take time, I think. No? How much time it will take? 5 minutes? Okay, you do one thing. Do do everything. Yeah. Do the question. Can you do it? I think you want my help.
I I'll do it, sir.
Okay, perfect. You got the concept, now. If you didn't get the concept, please ask me. Patrick,
Yes,
you
sir.
got the concept?
Got the concept. Got it, sir. Got it, sir.
Very good. Very good. भैया कूलर से दूर रखो कूलर का पता नहीं ना भी इलेक्ट्रिसिटी बहुत फ्लक्चुएट हो रहा है Hey. Hmm? क्या क्या नहीं, मैं केला खा के आया आज। मैं खा लूंगा बाद में। हाँ हाँ। यश छटवाल कौन है ये? अच्छा का। एडिक डन।
Almost.
Okay, Edric.
Yes.
My question was like I was explaining this thing to you now. Okay, for example, the hydrogen atom, like hydrogen atom remains in the first shell. If it will if it will absorb the energy from outside, and during that absorbing that energy, it will excite it to some state. For example, P fund line means N5. Okay, are you with me?
Yes, sir.
No. Hmm? Now, obviously, it will get come back to the same N1. So my question was that did hydrogen always releases ultraviolet rays? Because if it is coming from 5 energy excited level to the first energy excited level, it will like coming back to the first always ultraviolet. So my question
Always
was
lineman only. That means always lineman. Always lineman.
always line means always ultraviolet. So my question was that can you see the light emitted by the electron?
Since it's ultraviolet, we cannot.
But it's not true. We can see the light because when an excited electron come back to this original position, it's not coming directly to that. What I'm trying to say, for example, if electron get excited to the 5,
Yes.
then first it will go to the 4. It will not directly come to the first place. Like it can go to the 4, then like now it came from 5 to 4.
Yes.
Okay, then it can go to the 3. So when it is coming from 5 to 4, infrared, far infrared, then 4 to 3, infrared, 3 to 2, visible, and 2 to 1, ultraviolet. It can travel like that also. Are you with me? No.
Always travel like that, or only sometimes it travels like that.
It depends upon the experiment also, and it depends upon the what situation you are giving. Okay, so it like coming back from 5 to 1, not always true. If it is 5 to 1, then ultraviolet we cannot see the light. But in the case of discharge tube that we did in the line spectrum of hydrogen, we saw that there are some nanometers are there which is resemblance to the infrared also. For example, can you see that page again? What the page? Yeah, page number 55. Can you see that, please?
Yeah.
You can see that we have one 410 nm, 434, 486, and then 657. 6 657 is basically what? 657 nanometer is means we have different type of wavelength. If it is coming back to the only from to the ultraviolet, then it won't be that much difference will be there. Okay, why? Because the coming back of the hydrogen path is not fixed. Means it can come to 5 to 2 to also. It can come to the 5 to 3 also, depending upon the how much electron, how much energy it will lose to come back to the orbital shell.
So like basically that you're saying that if an electron is at n1 is n is equal to 5, and then to come down from n is equal to 5 to 23, and if n is equal to 1, there are so many steps like 5 to 4, 4 to 3, 3 to 2,
Yes,
1.
it's not necessary that it will only come back to the directly to the first place. So if it is directly to the first place, ultraviolet we cannot see. But if it is coming to the second, then
Visible.
visible range line we can see. Are you getting my point? No, you're
Yes,
not
sir.
getting my point.
Yes, sir. We can. Yes.
Okay, so remember this thing. This question they can ask you that will hydrogen electron which got excited, will it give the visible range light? It can give. It's not necessary that it will directly go to the first electron, first orbital shell. Are you getting my point?
Yes, sir.
Okay.
Yes.
So is your concept is clear now? No.
Yes, sir.
Okay. You're done with the question?
Wait. Yes, sir. I'm done, sir.
Done?
Yes, sir.
Okay. So now we'll end this class till here only. Tomorrow we'll do more question about that. Okay?
Yes, sir.
Okay then, Edric. Because the next topic is a little bit big, it will take time. So we'll end the class today only. Today is no homework, and then we'll meet on tomorrow. Till then, bye. Edric.
Bye, sir. See you tomorrow, sir.
Bye. Bye, Edric. Okay, guys. 1 minute break, 2 minutes break, and then come back. We'll start the maths class.